Alright, this is lecture 6 over chapter 6 in your book. This one's going to be pretty thorough, pretty lengthy. Alright, you might have to pause and come back and forth a couple times. But we're going to go over series parallel combination circuits. So chapter 4 we did series circuits, chapter 5 we did parallel circuits. Now we're going to put those together. Alright, and we're going to learn some different ways and techniques of solving circuits too. We're going to cover a Wheatstone bridge, we're going to cover Thevenin's theorem, we're going to cover maximum power transfer, and we're going to talk about superposition, different ways of solving some combo circuits, or just rewriting a circuit down into its most simplest form. Alright, so most of the circuits we use, they're not all series, they're not all parallel, but they are a combination of series and parallel. So we're just kind of combining. Alright, so in this scenario, right, we went from a series and now this is a parallel. Alright, but now we're going to talk about a combo circuit. And then in order to solve a combo circuit, anytime I say combo circuit, we're talking about a circuit that involves series and parallel connections in it. Alright, we need to find the simplest equivalent circuit possible. Alright, so we can write it down to eventually one source and one resistor. So that way it's characteristically the same as essentially we want to break it down to like a one series type circuit, and that way it's simpler. Does the circuit do the same functionality? Absolutely. But we want to make the circuit as simple as possible. So you might have to pause and retrace these. I would make sure that you have a lot of details in your notes for this one, especially when you take the lecture quiz, and since this will be on one of your major quizzes as well, I'd make sure that we know what we're doing on this case. Alright, so for us, right, if we have two resistors in series in this case, I can simplify this series connection down to what? One resistor by adding these two resistors together, right? We have R1 and R2. It's a series combo, so I can add them together, and now I've made the simplest equivalent circuit that I possibly can with this. So that's the goal, what we're going to do here. Because what happens is when you plug something in on the left hand side, those two terminals, the box doesn't care what's behind there. If there's 50 resistors or 10 resistors or whatever the components are, it only knows those two terminals. So when I think of a box like this, what I want you to think of like your home stereo receiver, where you plug in like an HDMI cord, or you plug in your audio and visual cables, or your component cables, or your speaker plus minus. Alright, we're going to talk about that when we get into maximum power transfer. But your speaker doesn't care what's going inside your stereo receiver. It just cares that it gets the right resistance and impedance matches so that it can output the sound for you. So that's really what it is. Like, your cable box is like a black box, but whatever you plug in to it, it doesn't matter what's going on inside the box, as long as that resistance that's coming out of it is characteristically the same. Alright, so what do we have here? We have two parallel circuits now, right? We remember these from chapter 5. We can combine these and make an equivalent circuit. Since it's two 1K resistors, right, you should know and remember the total parallel resistance has to be less than 1,000 ohms in this, right? Has to be smaller than the smallest resistor. But we can make it so that it's what? 500 ohms. Okay, so between these, like I said, once again, if you are plugging in something, it doesn't care what's inside the box. It just cares that the resistance is correct. Same when you plug in like your vacuum cleaner or something else, right? It doesn't care about what the motor is or anything like that. It just matters that the resistance, or we're going to refer to it sometimes as the impedance, is called. Alright, so that it gets, we get the right current flow. Essentially, that's really all we're looking for, so we don't trip your breaker or do something else wrong in your house. Alright, we'll talk about this a little bit more in class if everyone's getting a little lost here. But that's essentially what we're doing. Now what? We have, this is where you need to really start analyzing your circuits and understanding the relationship that's going on between the resistors. Now we have three resistors. We have R1, R2, and R3. And there's different relationships, and you have to do them in a specific order to solve the circuit. Alright, we want to take these three resistors and write them as one circuit with one resistor. So what's going on here? I want you to see if you can identify real quick. R1 and R2, what's the relationship between R1 and R2? They're in series. So we would do that series connection first, right? That series connection is in parallel with R3. Does everybody see that? If R1 and R2, we'd have to do that connection first and find that total resistance. That total resistance between R1 and R2, right, it's 3.7 kiloohms. That's in parallel with R3, which is 4.7. But when you do these circuits, when you're solving these on your assignments, okay, and on tests, I want you to do them step by step and draw them step by step. It will really help you understand that. I know some of you guys are gonna want to try and do it all in your head, and that's fine, but you could get lost. Draw them step by step. And what do I mean? Start, pause the video, draw this exactly as you see it, and then I want you to draw the next circuit and explain in your notes what we did between these two. What did we do? Since R1 and R2 were in series, we were able to add those two resistors together. So we got 1 kiloohm plus 2.7 kiloohms gave us 3.7 kiloohms. Now we have another relationship, that series relationship of R1, R2. It's in parallel with R3. So now I have to solve this in parallel. I have to get the parallel resistance, right? Hopefully you remember how to do that. I'm not going to break it down into too much detail, right? But we should be able to take like 3.7 inverse plus 4.7 inverse, and then that entire quantity inverse. If you don't understand what I'm talking about, go back to chapter 5 and revisit how we solve for parallel, total parallel resistance. But we get this total parallel resistance, and we get 2.07 kiloohms. And how do you know if you did the parallel resistance correct? All right. Remember, the parallel resistance has to be smaller than the smallest resistor in parallel. The smallest resistor in parallel is 3.7 kiloohms. It has to be less than that. 2.07 kiloohms is less than that. So most likely we did our calculation correctly. So we can see, okay, starting from the first schematic where we had R1, R2, and R3, how we can break this down and make it into one simple circuit. All right, you will have questions on your test for this. You will have questions on your final for this. You will also have questions on your lecture quiz for this. Please, please, please make sure that this is well documented in your note on the breakdown of going through this, because I'm going to give you a circuit that is much bigger than this, and you're going to have to go step by step. You understand whether you got to knock out a parallel version first, or whether you got to knock out a series version first, or what. Okay, but so that box, once again, your stereo receiver, you plug in your jack. It doesn't know what's inside the box. It just knows that it's getting the right impedance or the right resistance when it's doing it. All right, let's do another one here. As we go through these, let's take a look at the steps here and review chapters 4 and 5. So, chapter 4 was series circuits. What do we need to recall from series circuits? We need to recall that the current through this series circuit remains the same. So regardless of how many components I go through, if they are all connected in series, okay, they will all have the same current. And then we did what in chapter 4? We had to find the voltage drops across each resistor. So, and then what? We had to use Kirchhoff's voltage law. The sum of the individual voltage drops have to equal the total voltage. So make sure that you understand the series piece, because when we do combo circuits, you're going to have to treat the series like series, the parallel like parallel, and then be able to combine them together. So very important when we did that. Remember, for parallel circuits, it's sort of the opposite. Current has what? Multiple branches. So current can be split, but what happens to voltage? Voltage has to remain the same across the specific nodes in question. All right, so, and I'll point out when we do all of our specific examples of what we're talking about, because some of you guys are going to get confused when we have parallel resistors with a series one, and where you think the voltage might be actually the same. So we got to really make sure that we clarify that when we go through. But for Kirchhoff's Current law applied to parallel circuits where the sum of the individual branch currents had to equal the total current. So we can kind of see the similarities and the differences between parallel circuits. In series circuits, if you can understand those differences and when we apply them and how we apply them, you will be completely successful. I mean, I would say out of all the chapters in this book, this is probably the most difficult and the one that everybody struggles with every year, is being able to bring these two circuits together into one. All right. So some basic steps for solving these. All right. What you should always do, step one, find the equivalent resistances. All right, look at the parallel connections that you can knock out right away, the series connections that you can knock out right away. Here's the biggest one. The last sentence in here is the most important one. I would take a lot of time when you're solving these and you will be much more successful. If you try to rush through these, chances are you're not going to be successful because you don't 100% know what you're doing. If you redraw the circuit each time you simplify it, it will make your life easier. Those of you that are going to be successful, you're going to be the redrawers. Those of you that aren't going to get this and struggle with this, it's because you refuse to redraw the circuit. So like the first 3 or 4 examples that I did, where I redrew the circuit for you, redraw the circuit. Okay? Then each time that you redraw the circuit, calculate the total resistance. All right, of whatever you combined, whether it was series or series or parallel. All right, but you need to work that circuit down to 1 resistor. Okay, like I've been showing you, work it down to 1 resistor. That's the total resistance. Then you do step 3. You're going to calculate the total current using Ohm's law, right? I equals V over R, but it's the voltage source. So it's total voltage divided by total resistance gives us total current. So make sure that that's what you're doing next. Then we have to calculate the voltage drop against any of the series resistors. Then we're going to do the voltage drop across the parallel section. And this will make sense as we do an example. I just want you to kind of have, and you don't have to write these verbatim. Don't write them word for word. Write them so that you understand them. All right? They don't have to be complete sentences, but I would write down the basic steps. All right? And then once we do this, we can find all the branch currents. It's easier to find the branch currents. We can use it one of 2 ways, right? We can use a current divider, which can sometimes be confusing. We'll have an example where we're going to use a current divider. Or, as long as you know the voltage and the resistance there, you can apply Ohm's law. A lot of this can be done just by applying Ohm's law and by applying KVL and KCL. All right, and then make a summary of the voltage drops and check with KVL and KCL. Check all the branch currents. Do they add up to the total current? Do all the voltage drops add up to the total voltage? All right, so very simple self-check. Don't try to rush through these circuits. This is as hard as it gets at this class. All right, there's a whole new level when we take the university level course. All right. And it's all calculus based, so it takes it to a whole new level, and we apply KVL and KCL and current loops and mesh currents and all those sort of things to do those sort of things. So let's take a look. This is a breakdown. This is just a snippet out of your book. All right, but just understanding what the relationships are and how to approach them. All right. Always try to get the total resistance first, then we can get the total current. But to understand the total resistance, we have to look at the relationships here. All right, we're looking across the terminals AC and B. All right, but we want to take a look here. We have R1, R2, and R3. I'm on all the way on the left-hand side, and starting on the left, we're going to move to the right and simplify the circuit. If we look at that, R2 and R3 have what type of relationship? They're in parallel, right? We can tell that because of the way the nodes are. So R2 and R3 are in parallel, and that parallel combination is in series with R1. So all the way on part D on the right hand side, you can see that to find the total resistance, we would find R2 in parallel to R3, so get that parallel resistance, and then add it to R1. All right, C is important for us to understand where the currents are. Notice that I total only goes through resistor 1 in this scenario, and then we have 2 branch currents, I2 and I3. And we need to know that I2 plus I3 has to equal IT. And why do we call it I2 and I3? Because it's going through resistor 2 and resistor 3. That's why we're calling it current 2 and current 3. Alright, look, and what I want you to know where everybody gets confused, there's two different voltage drops here. Alright, if the voltage source with 12 volts, the voltage drop across R2 and R3 is not 12 volts. It's 12 volts minus whatever the voltage drop is across R1. So there's still two voltage drops going on here, not one. So R1 does not have 12 volts dropped across it, neither does R2 and R3, if I said Vs was 12 volts. So we just got to make sure that we pay attention on this case. Alright, let's say we add another resistor here. This is just so that you understand how to approach these circuits. We have R4 and R1, that relationship, they are in series. That series relationship, okay, is added to R2 and R3 are in parallel. So we can take R1 plus R4 plus the R2, R3 combination. Once we calculate the parallel resistance between R2 and R3, it's in series with R1 and R4. Alright, so we'll work through these, and make sure, please don't hesitate when we got class or lab to ask me some questions if you're getting stuck on these. But when you do ask questions, please come with specific examples written down. Don't say, hey, in lecture you were talking about this. Have it written down, because there's like 90 some slides in this one. I'm not going to remember every slide. But if you come with a circuit drawn out, we can work through it. Okay, so just be prepared. So if you ask a question, just make sure you're prepared. I will be more than happy to work through it with you. Now what did we do here? We're making the circuit more complicated, aren't we? So on the left hand side, now we have what? R1, R2, R3, R4, and R5. What did we add in here? We added R5. R5 is now in series with R2. So now R2 and R3 are not in parallel. The combination, or the series of R2 and R5, that total resistance is in parallel with R3. So we have to be careful on the relationship piece here. And this is why it's important to redraw the circuits. This is not a good example, this is out of your book, of showing how to redraw the circuits. This example is to just show the relationship between the total resistances as we approach this. Okay? You will redraw the circuit each time to simplify it down. But we have R1 and R4, those are in series. R2 and R5 are in series, and that series combination is in parallel with R3. Once we get that combination, the R2 plus R5 in parallel with R3, that value will then be in series with R1 and R4. Alright, so we got to go step by step, piece by piece when we're doing these. Now what? It gets even more complicated. What did we do? We made R6 in parallel with R1 and R4. So now we have to add R1 and R4 together and then do a parallel combination with that total, and then that's in series with the rest of the circuit that we see there. So remember, this is just in your book that's kind of showing step by step of how we can start making these complicated. Alright, but knock out your series combos first if you can, and then do parallels, and that might create another series, or it might create another parallel. Alright, so you just got to be able to bounce back and forth, step by step, one circuit at a time, or one component at a time. Do not try to attack what you see in diagram A, or in figure A. Don't try and do the whole thing at once. Alright? Until you get these down. I mean, if you can see like what is shown in figure C, where RT is R1 plus R4 parallel to R6 plus R2 plus R5, which is in parallel with R3. You can't plug it in your calculator that way. Alright, but you can write it out step by step. Let's take a breakdown of this so that we kind of understand. I'm not going to try to give you something this involved on the test yet, but I will expect you to do something like this. All right. So we're going to take, this is a delta. We're going to talk more about this when we get into transformers, but this is a delta. So remember, a delta is a Greek letter. And also, it's in the shape of a triangle. So that's why we kind of see this delta connection, all right, from the transformers. So this circuit can be written 3 different ways, and we're going to do all 3 together here. We can see what the circuit looks like from the connections A to B. We can see what the circuit looks like from the connection B to C, and we can also see that the circuit looks differently from A to C based on the connections, and it changes all the series and parallel relationships. So we're going to see this circuit right now. We're going to write the equation for the nodes if we were looking only at terminals A and B. So the perspective from A and B. This is why it's very important that you understand how to redraw this circuit. Okay? If you can understand how to draw this circuit, then you actually can really grasp what's going on here. So we want to see what's going on from the perspective of AB. Well, the perspective of AB, if we redraw this circuit, is going to look like this. What's across AB is resistor 1. Then if I'm still looking at AB, if I go from the left-hand side, right, I'm going to have between B and C is R2. And then between A and C is R3. Notice that in this particular scenario, R2 is in series with R3, and that series combination is in parallel with R1. Hopefully you can see that. And this is from the perspective of terminals A, B. From if we were to plug something into A and B, and what we would read out. In your calculator, it translates down to this. You would have R1 inverse, and then you would have to do the quantity first of R2 plus R3 because they're in series, then inverse that, and then take the inverse of that entire piece in your calculator. Alright, so if you had numbers, there's how you would substitute that in your calculator. But what's very imperative, and I want you to make sure that you have this in your note because we're going to do all 3 versions of this. I really, really, really want you to be able to draw the original circuit and then draw its equivalent circuit. You should be able to, if I gave you values, write this as one single circuit. Okay? Let's take a look now. Same exact original circuit, but now we're going to look from the perspective across terminals A and C. So if you turn your head, I guess, and you look up, we're looking if we plugged into A and C at the same time, what does this circuit look like? It changes the perspective of the circuit. Now, if we're looking at AC, okay, R3 is across the terminal AC, and R1 and R2 are now in series. So see how that changed from the previous one? What the different series combination is versus the parallel piece with it? Okay, now R3 is in parallel with the R1 plus R2 series combination. Okay, please revisit parallel if you're getting lost here, because parallel means they're sharing the same nodes on both sides of the component. Series means they're only sharing one node. So R1 and R2, they only share node B. But notice R3 and that their combination of R1 and R2, they share at node A and node C. Alright, so if you were to write this one in your calculator, you'd have R3 inverse plus, then you have to do the parallel combination there of R1 plus R2 inversed, and then the quantity inversed. Okay, so R1 and R2, that's the series piece. That's why they get the extra set of parentheses there. Alright, lastly, let's take this same exact circuit and look from the perspective of B to C. We've done 2. Why don't you give this one a shot? Why don't you pause the video and see if you can draw the relationship. Okay, I'm going to go through it here, but give yourself a chance. See if you understand what's going on. We're looking from the perspective of B to C now. So what does that look like? What's across B to C is R2. Now, that makes it so R1 and R3 are in series together. And that series combination of R1 and R3 are in parallel with R2. So mathematically you need to add and find the series first, get that resistor, that total resistance, and then take it in parallel to R2. Okay? So RT is equal to R2 inverse plus R1 plus R3 inverse, and the whole quantity gets inversed there. So now we're going to solve this circuit. Alright, sorry I don't have all my animations down correctly where my ITs are going, but we're going to solve this circuit for RT, IT, I1, I2, V1, V2, V3, P total, P1, P2, P3. Remember, P is for power, V is for voltage, I is for current, and R is for resistance. So this is a perfect series parallel combination circuit. You will have one like this on your quiz. On your quiz 3, you will have one on your final. Alright, I will hound you to death with this. This is a basic one. This shows me that you understand really what's going on here. Okay? So, what's the first step? We need to find total resistance. What are you asking yourself in your head? What's the relationship between all the resistors? You should see that what? R2 and R3 are in parallel with one another, and that combination is in series with R1. Alright, so I'm going to redraw the circuit. Okay? To find RT first, okay, as we go through this, I just talked about, RT is R1 plus that R2 inverse plus R3 inverse, all inverse. That, remember, anything with the inverse, that's the parallel combination. And if we just substitute that in right away, we're able to see that RT is equal to 980 ohms. Just doing that series parallel combination on the circuit there. Okay? But next, or we can do the equivalent circuit, okay, and this is the method where we want to break it down. This is where I'm saying redraw the circuit. So the first part I showed, man, if you can see that, do it and make sure, that you're plugging the numbers in correctly. Else, if you can't see that right away, like writing that RT equation out and just substituting it in the calculator, this is what I mean by redrawing the circuit. So what have we done? We've gone from the first initial circuit or schematic, and what did we do? We found the parallel combination between R2 and R3, right? And I've given that to you down before. So R parallel is going to be 800 inverse plus 1200 inverse, all inverse, and we get 480 ohms. Does 480 sound right? Yes, because it's smaller than the smallest resistor in parallel. The smallest resistor in parallel is 800 ohms, and 480 is smaller than 800. So now what did we do? We made that parallel connection kind of go away. And now what? It's in series. That 500 ohm resistor is now in series with the 480 ohm resistor. So now I can rewrite that by adding the 500 and the 480 and getting the 980. So my total equivalent resistance, or my RT, is 980 ohms. So I've shown you two different ways. The first one, if you can visually see the relationship between the resistors, substitute it into your calculator, alright, and go right forward and get 980 ohms. If not, if you need to break it down, and I think this is the better method for you as you're just starting to learn, redraw the circuit. Do that parallel combination first and redraw the circuit with the equivalent resistance of 480 ohms. Then you can see that 500 and 480 are in series with one another. Add those together and redraw the circuit. Why do you keep this redrawed circuit? Because you can still find the total current with this and the total power. It's advantageous for you to draw this equivalent circuit of 12 volts and 980 ohms. You can still do some major calculations here just based on that piece. Alright, so the same circuit, I just moving forward with the slide, and I'm given our equivalent resistance here. Alright, so why did I keep these two circuits that we redrew? Well, the first one's going to help me find, total power and total current. The second one's, once I know total current, I know the voltage drops. Alright, so it makes it easy. So redraw these circuits, and that'll help you do some calculations. So we can find total current now, the voltage drop across resistor 1, total power, and the power across resistor 1. Alright, so current for us now, total current is just the total voltage, which is the voltage source, divided by the total resistance. So It's Vs divided by RT, and we calculated RT to be 980. All right, so 12 divided by 980 is going to equal 0.01224 or 12.4 milliamps. So that's our total current in this circuit. We're going to use that total current later if we can use a current divider to find the parallel branches. All right, but next, now that total current is going to help us in the second circuit over there as well to find V1. But since we know the total voltage source, right, it's 12 volts, and we know the total resistance for this circuit after doing the series parallel combination calculation is 980 ohms, we're actually able to find the total power using Watt's law that incorporates voltage and resistance of V squared over RT. So we're going to have 12 squared divided by 980, or the total power for this circuit is 146.93 milliwatts. Next, we can find the voltage drop across resistor 1 by using Ohm's law. Voltage equals current times resistance. Now we have to use IT, and we have to use the specific resistor R1. So V1, that's the voltage drop across the resistor 1, so I have it labeled for you up there, is really just the total current, and make sure you use it in amps, not in milliamps when you do this calculation. So use 0.01224 times 500. The voltage drop across V1, or the voltage drop V1 is 6.12 volts. That's the voltage drop across resistor 1. That's important because that's going to help us know the voltage drop across that parallel piece. We can use Kirchhoff's voltage law. We're going to use that in a second though, so important stuff. But lastly, since we know now everything about what's going on at R1, we can find the total power at resistor 1 that is dissipated. Power equals what? We know V1 and we know the total current now. Okay, I could have used the I squared R as well. I could have used total current squared times 500, but we can use this one as well. Power is VI, so 6.12 volts times 0.01224 amps. And the total power dissipated, all right, in resistor 1 is 74.93 milliwatts. All right, we're going to keep going now, but helping and having these equivalent circuits is really beneficial for us. All right, so I'm going to bring over what we just calculated, our IT, which is 12.24 milliamps, and our V1, which is 6.2 or 6.12 volts. All right, so we can use Kirchhoff's voltage law, like I said, to find V2. All right, so we can use Kirchhoff's voltage law. Remember, that's the sum of the individual voltage drops have to equal the total voltage. So since the total voltage is 12 volts, and I calculated the voltage drop across resistor 1 to be 6.12 volts, we can subtract those. So the voltage drop across resistor 2 is 5.88 volts. Okay, that's really going to be beneficial to us now. That's the voltage drop across resistor 2 we just calculated using 5.88 volts. What does that tell you about the voltage drop across resistor 3, where V3 is? What's the relationship between R2 and R3? They're in parallel. What do we know about parallel resistors? The voltage drop across parallel resistors is always the same. So therefore, the voltage drop V2 equals the voltage drop V3. So V3 also equals 5.88 volts. So now we found V2 and V3. That's advantageous because now we can just use Ohm's law to find the currents I1, which goes through R2, and I2, which goes through R3. We can use Ohm's law. V over R equals I. And it's voltage and resistance specific to that resistor. So I1 is going to be V2 divided by R2, or 5.88 divided by 800, which is going to get you 0.00735 or 7.35 milliamps. All right, if we take a look, that helps us get power too, now that we know that voltage drop. So we can take that voltage drop of 5.88 squared divided by 800. So we're applying Watt's law there. And power is 43.22 milliwatts. We can do the exact same thing for I2 over here. I2 is the current going through R3. So the voltage drop across R3 and the value of R3. So current is voltage divided by resistance. So 5.88 divided by 1200 ohms. We get 4.9 milliamps. You get 0.0049 amps, but that's 4.9 milliamps. So that's I2. So those are our two branch currents, right? I1 and I2. If we add those up, they better equal what? IT. Do they? All right, 7.35 plus 4.9 gets pretty close to 12.24. So remember, they're not going to be 100% exact because it depends on the amount of decimal places you're using when you do these calculations. But they should, if they're like extremely close, you're good to go. And then now we can calculate the power dissipated in that last resistor, the voltage across resistor 3 divided by resistor 3, so the voltage squares. It's still Watt's law, V squared over R. All right, so we're going to take 5.88 squared divided by 1200. You're going to get 0.02881, which is 28.81 milliwatts. Make sure that you're doing all these calculations. Pause the video, write everything down, redraw the circuits, get your calculator out, you plug in the numbers, and make sure that you're getting the same values. Okay? So let's verify everything. We can check all these with KVL and KCL. So I've given you the two equivalent circuits that we've redrawn at the bottom based on this specific circuit. Okay? And then we have what? IT is 12.24. Well, I1 and I2 are the branch currents, so those two combined need to equal 12.24. If we look at the total resistance, we calculated it. Look at the voltage drops, KVL. The voltage drop V1 plus the voltage drop V2 needs to equal 12 volts. They do. 5.88 plus 6.12 is 12 volts. And then the sum of the three powers need to equal the total power, and they do. One thing I want to reiterate on this, okay? R2 and R3 are in parallel and they have the same voltage drop. But when you have a series resistor before them, you need to find the voltage drop of that series resistor before them before you can assume what the voltage drop. Don't assume the voltage drop across R2 and R3 is 12 volts here. It's not, because R1 is in the way and there's a voltage that drops through R1 before it gets to the R2, R3 parallel. So really make sure that you know this. Now what I'd like you to do, you may or may not do this on your own, is go back and redraw this circuit again, just the original one, and resolve this on your own. If you can resolve this on your own, alright, give it your best shot. If you can resolve this on your own, you got this down. Alright, I would do it a couple times until you can resolve this same circuit on your own. So remember, engineering takes a lot of practice and a lot of working through problems. Working one or two problems isn't going to make it solidify for you. Okay, we got a lot to do in this chapter as well. We're maybe a third of the way through the lecture now. All right. So also, what's this? We got a circuit board. So this is like one that you guys might have soldered in a previous class. Draw the schematic for this board and give the equation for the relationship of the resistor branches. So we got to be able to take this schematic. Notice there's terminals A and B, and then we got 6 different relationships, and we want to draw the schematic and understand all the different series and parallel combinations that are going to occur here. Alright, so I've put that same circuit at the top, and we've translated it to a schematic. This one you pretty much can draw it as you see it, almost, alright? Where the connections are and where the nodes are. We can see that R1 and R4 are in series. R7 has to go to terminal B. We can see that R2 is going to have some sort of parallel connection between R3 and R5. Alright, and then R6 has a parallel connection to R5 there. So stare back and forth between these two drawings so until you understand how to go from what's in green, the printed circuit board, to the schematic in diagram A. Alright, so now we have the schematic down. you need to look at what relationships can we eliminate right away. Alright, we can see that we can do R1 and R4, they're in series, we can add those and get a resistor. And then we can see that R5 and R6 are in parallel. We can combo those with a parallel combination and get that value. And then that value will be in series with R3, and then that'll be in parallel with R2, and so on and so forth. I don't want to overwork this and confuse you right away. But we might want to redraw the circuit a little bit differently here. Alright, so R1 and R4 still in series. R2 is in parallel with R1 and R4. And then R3, alright, we have R5 and R6 that are in parallel. That's really just rewriting that one. Okay? Then we can simplify the different groups. So like I said, R5 and R6, we're going to consolidate that down to one resistor. So finding R5 and R6 in parallel. Okay? Once we do all this, we can write out one big equation. Now this is much easier to solve when we have numbers, but you should be able to look at this diagram and actually write the equation down below based on what's in series, what's in parallel, and all those different relationships out. Sometimes you got to redraw the circuit, sometimes you should be able to visually do it. So you can pause the video and kind of study through on that one. I'm more interested in making you solve it and rewrite it at the same time. Let's do one together though. Alright, so take the time, draw this circuit down, and then we're going to do it. For these, the best bet we are going to move is right to left. We're going to move kind of backwards here. We're going to go right to left. So I'll give you a second to draw this down and then go ahead and hit play because I'm going to work through it. Alright, the first thing we should see is that R3 and R4 are in parallel. So we got to change that parallel combination. Okay, or get the parallel value, and then that's going to be in series with R6. So R4, we have 12 ohms in parallel with 12 ohms, and we're going to redraw that circuit. So I've gone back. Let's take a look. Let me step back here. All right, I'm going to redraw the circuit. Every single step, we're going to redraw the circuit. So we're going to find that parallel combination. 12 ohms in parallel with 12 ohms. Okay? You should be able to get 6 ohms when you do that. Don't think it's 12. Remember, they have to be less than 12. So when you do that, you get 6 ohms. And now we're going to redraw it again. That 6 ohms is in what? Series with that 4 ohm resistor R6. So we're going to take 4 plus 6, and we're going to get 10 ohms, and we're going to redraw the circuit. Now we've redrawn the circuit, and now we know that what? That's 10 ohms, that resistor. That 10 ohm resistor that we just calculated is in parallel with R5. R5 is also a 10 ohm resistor. So we're going to find the parallel resistance, and then we're going to redraw the circuit. So we have 10 in parallel with 10, okay? And we get 5 ohms. So that resistor we just calculated and simplified down, so it's between terminal A and B, is 5 ohms. Now what's the relationship? We have R1 is in series with that whole combination piece that we just did, that's 5 ohms, and that's in series with the 30 ohm resistor. So now we can just take 15 plus 5 plus 30 and write it as one resistor and get 50 ohms. So that total equivalent resistance right there is 50 ohms. Does that make sense? So I'm going to step back through a couple slides here and just re-show you, okay? Not that one. Alright, this. So we've taken this entire circuit here, we've moved right to left and written it as one voltage source with one resistor, and that entire series parallel combination breaks down to 50 ohms. Alright, so we just kind of went through all that. We go through this a couple times, see if you understand what's going on. And then if we wanted to find the total current, alright, we have the total voltage, we have the total resistance. Current is V over R. So 50 divided by 100 is 2 amps. Okay. So if we were to put a meter on all of those, we'd be able to see all the different voltage drops that occur. And this kind of relates back to the first example we did, where we got 2 guys in parallel, right? And then we have that first leading resistor. So this is kind of like the first real big in-depth example where I made you calculate all the currents, all the powers, all the voltage drops. You can look at the relationships here and how that happens. So notice on the meter, we got 10 volts total across that battery source. And we have that first resistors R1 and R2, they're in parallel. Their voltage drop is 5.15, and they're in parallel, so they both share that same voltage drop. To get the 4.85, right, we have to do 10 minus 5.15, and that gives 4.85. R3 is in parallel with a series combination of R4 and R5. If we look across R4 and R5, that series combination has to equal the total voltage of 4.85. That's the total voltage drop across R4 plus R5. So if we see that 1.58 plus 3.27 equals 4.85, because their series combination has to equal the same voltage drop as R3, because that series combination of R4 and R5 is in parallel with R3. I'm not going to work through the examples so much on this one. I think you guys can take a look at it just knowing the voltage relationships if we go that route. So you can pause the video and work through those and see if you're getting through all of them. Okay. Same with if we take a look at the readings across node A. I'm leaving these in here for you to help solve, and if you have questions, you can come ask me and we can work through this. Alright. But what I would do, just looking at this circuit to calculate those currents, alright, notice that we have R4, R5, and R6. I would do those are in series first. That series combination is in parallel with R3. Alright, so then get that total resistance, and then what you calculate there is in series with R2. Okay, so you'll get a total resistance there, and then you can use R1, okay, being in parallel with that, and then you would get the total resistance, and you have the total voltage, and that'll give you the total current, which is 26.5 milliamps. So work through this problem. There's a couple problems I want you to work through on your own in here. This is ones we would do on the board, and if you have questions on them, ask me when we are, you know, like face to face, or during office hours, or during when you before class, or if we want to ask a question before we get going, we can go over these as well. Okay, just make sure that you have it written down, like I said, what the problem is, and we'll work through it. Alright, let's get on to loaded voltage dividers. Okay, these shouldn't be anything super new to you. This is because we talked about voltage dividers extensively in series circuits. This is how your multimeter works and how it gets the correct voltage reading. Okay, if we wanted to look at the output voltage across R2, remember, this is just review. R2 divided by the total resistance times the voltage source would give us that drop, okay, across R2. And the same drop across R2, it would be the same drop across R3 because R2 and R3 are in parallel here. Okay? So, a voltage divider with a resistive load forms a parallel combination. So R2 and R3 are in parallel. What this means for us in understanding is we call this a loaded voltage divider because we have RL, we have a load sitting in parallel with R2. So what does that load do? It reduces the total resistance from node A to the ground. Remember, the more resistors we have in parallel, the smaller the total resistance value will be. Resistor, as we add more in parallel, total resistance goes down. If we add more resistors in series, total resistance goes up. Okay, so we want to find the voltage across resistor 3. Alright, so what we have to do is that voltage drop is now being affected by that parallel combination. Okay, the R2 and R3. So we can use a voltage divider here, but we have to calculate what the parallel relationship is between R2 and R3 first. Then that'll be our top resistor in our voltage divider. So our parallel here between R2 and R3 is 470 ohms. Alright, so 470 in parallel with 22 kilo ohms is 387 ohms. Notice 387 is smaller than 470, so we are good. So remember, in your calculator, that's 470 inverse plus 2200 inverse, all in parentheses, and that's inverse to get the 387. Alright, now we can use a voltage divider. We can use that 387 that we just calculated, divided by that total resistance, 387 divided by the 330 plus 387 times 15, okay, and we should end up getting a voltage of 8.10 volts. This isn't really different than what we did with series circuits using a voltage divider. All we're doing is adding a resistor in parallel with R2. So you just have one more step. You have to find that total parallel resistance before we find out that voltage. Now, what we're really trying to find out is what a stiff voltage divider is. And what we're looking for is what value of RL, a load resistance, can we really add on there that makes no difference for the voltage drop. That's how your multimeter works. It has a it's like a 10,000 kilo ohm resistor in there. The larger the resistor, so because when you're taking like voltage drop readings using the multimeter, right, that probe, you're adding a resistance, but you need to add a high enough resistance so that you're not impacting the voltage and getting the reading. So what we do is we add what we call a stiff voltage divider, and that's one in which the total resistance is nearly the same as the no load voltage. So if we didn't have RL on there, it would mean, and we calculated the voltage drop across R2, and then we add RL on there, and we want the voltage drop across R2 to still be the same. So we have to find a value of RL, and it's a really high one, so that we are not impacting the voltage drop. So that's really what a stiff voltage divider is. Okay, so we have to make sure that RL is really big, and we will not impact the voltage drop there. Okay, so in this problem we're just going to calculate what value of RL will make this divider a stiff voltage divider. Alright, rule of thumb for us, RL is going to be 10 times whatever value of R2 is. If we can go 10 times the value of R2, we've got a stiff voltage divider, and we will not impact any voltage reading there. So in this particular scenario, we're saying R1 equals R2, both are 1000 ohm resistors or 1K resistors. So we have to take 10 times 1000, therefore RL needs to be 10,000 kilo ohms or greater. So that gives us a stiff voltage divider there. Alright, if we needed to calculate that, I've put the math up here for you. Okay, but we don't really want to impact the load. Okay, so if we take a look, the voltage divider RL with 10,000 ohms, okay, and we use a voltage divider there, we had to do a parallel combination, we get 0.91 kilo ohms divided by 1 kilo ohm plus 0.91 kilo ohms times the voltage source, we would get 0.476 times Vs, okay, and then if we did it with no load, we would get 0.5 Vs. So notice they're very close, right? 0.476 and 0.5 are relatively close. Alright, so it's pretty much 95% of the unloaded voltage. So using 10 kilo ohms. Now, if we want to get it exact, we need to up the kilo ohms on that RL so that there's even a smaller impact. Alright, maybe get to 98% instead of 95. But that's what a stiff voltage divider is. Right, this is the Wheatstone bridge. Very important circuit. Those of you guys going to be electrical engineers and things like that, you're going to work on it in Circuit Analysis 1. Again, we use this to do a lot of different control voltages. Alright, so this is the same circuit. So in Figure A, we call it the Wheatstone bridge. That's how we normally draw it, and when you recognize it on a schematic, that's what it's going to look like. There's some different relationships. V out is a control voltage, and that's going to make sense when we start doing some problems. And then there's some relationships between the resistors. We're looking for a balanced or an unbalanced Wheatstone bridge, and I'm going to repeat this part over and over and over. Anytime you have a balanced Wheatstone bridge, V out is equal to 0. V out is equal to 0 if we have a balanced Wheatstone bridge. We're going to calculate V out here. In schematic B, it's the Wheatstone bridge redrawn so that we can understand what's going on. Alright, so for our understanding, when we redraw this, we can see that R1 and R2 are in series with each other. I'm sorry, R1 and R3 are in series with each other. So we can use voltage dividers to calculate the voltage drop across R1 or the voltage drop across R3. Then we see this, we can see that R2 and R4 are in series with each other. So we can use a voltage divider to calculate the voltage drop across R2 or the voltage drop across R4. Then we can see that the series relationship of R1 and R3 is in parallel with the series relationship of R2 and R4. So you should be able to start recognizing that as we go through. We can use multiple voltage dividers to solve these out and get the individual currents. Now the voltage divider piece that we're always going to look for, we want to find VA and VB. VA is the voltage drop across R3. VB is the voltage drop across R4. So we're going to have to be able to calculate those. We can see the relationship between the different currents, and we can see that for a balanced one, V1 has to equal V2, and V3 has to equal V4, and the currents I1 has to equal I3, and I2 equals I4. So if we're looking at it balancing, here is the relationship, and I don't want you to memorize resistor numbers. I want you to learn the series relationships and the parallel relationships. Because this is going to be drawn out multiple different ways, and it might be called RV, RX. They might have R1 and R2 on top, R3 and R4 on the bottom like you see here, or it might have R1 and R2 in series and R3 and R4 in series. You need to understand the fundamentals behind it, not necessarily the specific resistor value that's denoted here. But we do need to know the relationship. So in this relationship, R1 over R3 has to equal R2 over R4. Okay, R1 over R3 equals R2 over R4. And we'll use that relationship once again to do some basic calculations. You're going to solve this circuit and where it applies. So if we look at the Wheatstone bridge in general, it must consist of a DC voltage source. It has to have 4 different resistive arms. And we have to have 2 voltage dividers because we have to calculate the output V out across terminals A and B. Alright, that one's very important because we use that as a control voltage. And we're going to go through different things, but your scale, your thermostat in your house that runs your AC and your heat, and all those different things. We have variable resistors, so R2, sometimes we're going to call that RV for variable. That's the adjustable resistor where we can do. So when you're working on your thermostat in your house, that's where, hey, I want to set my indoor to 68 degrees or to 72 degrees. So you're setting a resistor value that's going to do that and adjust it to 68 degrees. Where R1 is going to be the resistor that changes based on temperature. So that resistor, as you go up and down in degrees, that resistance value changes. And the goal is to get a balanced Wheatstone bridge. So when V out is 0, all right, we've reached the temperature that you've wanted the air conditioning to be set at, 68 degrees. It turns off your air conditioning. If your the temperature in your house is set at 71 and you turn it down to 68, you've changed R2, all right, and it's going to be working. We're going to be getting an output voltage all the way until R2 and R1 create a V out of 0. So that's kind of how that works right there. We're going to do some simple calculations. So when the Wheatstone bridge is balanced, V out is going to equal 0. That means we're not sending out a control voltage. Okay. Another way to tell when it's balanced is the products of the resistance in the opposite diagonal arms are equal. What does that mean? That means R1 times R4, when that equals R2 times R3. If those are multiplied and they're equal, the Wheatstone bridge is balanced. So we have to find what value of R2 is going to balance the Wheatstone bridge. So we're going to say R1 times R4, set it equal to R3 times R2, and we're going to look for R2 here. So when we solve that algebraically, remember I'm using R1 times R4 equals R2 times R3 initially. When we solve that for R1, it ends up being R2 times the quantity of R3 divided by R4. So we can substitute our given values in, and you get 385 ohms. So you're going to take 330 divided by 270, multiply it by 470, and get 385 ohms. Alright, so we're actually going to take this and use a physical parameter, okay, a transducer, something that turns it into an electrical signal. That's what we're doing. We're taking some sort of resistance value, helping create an electrical signal in this case. So this is going to get into where we'll start talking about your air conditioning, or you step on your scale, okay, mechanical strain. So you're changing the value on your scale. So as you step on it, your weight changes the resistance value. The resistance value calculates V out. That V out translates into a weight that's displayed on your screen. Alright, we just talked about temperature with your air conditioning unit. Same with pressure. If we want to monitor pressure in a system and automatically control it. Alright, but the whole point is we're taking that output voltage, V out, and translating it into a signal that tells something to turn on or off. Alright, so we're going to do an example here that works through the thermostat in your house. So we have R1, R2, R3, and R4, and R2, 3, and 4 are all 1 kilo ohm. And your R1 is your thermostat, and it's set to 1000 kilo ohms at 25 degrees Celsius, and that's pretty standard with how we're going to take a look. How do we know that this is a balanced voltage or a Wheatstone bridge? Because V out is 0. And how else can we do it? Well, we can take what? R1 times R4. Does that equal R2 times R3? Yes. 1 kilo ohm times 1 kilo ohm does equal 1 kilo ohm times 1 kilo ohm. So we know that this is a balanced Wheatstone bridge. And I'm going to ask you a question like that on your test. Okay, I'm going to give you the 4 resistor values, and you tell me if the Wheatstone bridge is balanced or if it's unbalanced. So we also need to be able to find our Vx. Okay, it's going to be Rx divided by RT over Vs. What are we calling Rx and Vx? That's from where the thermostat is. Okay, our thermistor. That's our resistor that changes due to temperature. So what we're going to do on this calculation here is we're going to use the thermistor chart to calculate V out when the temperature is 50 degrees Celsius. Alright, so let's look at draw the circuit diagram out first, because there's going to be one on your notes that we're going to do here, and then you're going to have one on your lecture quiz. You're also going to have one on quiz 3, and you're going to have one on your final. So make sure that we understand what's going on here. So draw this circuit out, so pause the video and get that done, and then we're going to work through it. Alright, notice that the thermostat or the thermistor is 10 kilo ohms at 25 degrees Celsius, and we want to find what's going on, or what the output voltage is when the temperature is 50 degrees Celsius. So I've given you this big chart here. So what you need to do is on this chart find when the output voltage is 50 degrees Celsius, and that's going to give us the resistor value. So I've marked it on here. So right here at 50 degrees Celsius, our resistance is 3,601 ohms. Alright, so now we're going to use that in our equation. So our output voltage VA is going to be R3 divided by R3 plus our thermistor resistance, which is 3,601 times Vs. Okay, is that 3,601? Yes, because if you look at the chart, alright, and look where 25 is. 25 is up there and it's right at 10,000. So you have to use the value that's exactly on the chart for this example. Okay, so when you plug this in, it's going to be 10,000 divided by 10,000 plus 300, or 3,601, times the output voltage, or the voltage source, which is 12 volts in this case, looking at the schematic. So you should be able to calculate VA, and VB is going to be the voltage drop across resistor 4. So you're going to have R4 over R2 plus R4 times Vs. So you're going to have 10,000 divided by 10,000 plus 10,000 times 12 volts. Okay, so that's going to give you VA and VB. And to calculate V out, we have to take V out equal to VB minus VA. So when you get those calculations, I want you to do those in your calculator. Alright, we're going to work through a whole different example here. But VA is 8.8, VB is 6 volts, all right, and we find the difference between them, it's 2.8 volts. Okay, so V out in this scenario is 2.8 volts. Let's do a much more in-depth example here of the Wheatstone bridge. So make sure you draw this out in your notes, and we are going to go step by step how to solve through this. So, example being a resistor of unknown values connected to a Wheatstone bridge. The bridge parameters of the balanced condition are set as follows. RV is equal to 18 kiloohms, and the ratio of R2 to R4 is 0.02. What is Rx? Alright, so we got to see where Rx is and where RV is. So after you draw down the Wheatstone bridge, what we need to do is Rx divided by RV is equal to R2 divided by R4. So that's the relationship. Alright, we talked about that early on. Instead we used what though? R1 and R3 and R2 and R4. So that's why I said don't memorize which R it is. You got to look at the actual schematic and use the given R's. So in this case we're using X and V. Well, we know what the ratio of R2 to R4 is, right? It's 0.02, and we know what RV is. So we have to solve this algebraically for Rx. We know that Rx is R2 divided by R4 times RV. We've just solved it algebraically. Now we substitute in our values. Alright, so R2 over R4 is 0.02 times RV, which is 18,000 ohms. So Rx is 360 ohms. Pretty basic. I know it seemed kind of confusing seeing all those other ones before. Alright, the next one's going to take it a little bit to the next level. This is kind of like the last one we did. It says determine the output voltage of the unbalanced bridge for a temperature of 65 degrees Celsius. The thermistor has a nominal resistance of 1 kiloohm at 25 degrees Celsius and a positive temperature coefficient. Assume that its resistance changes 5 ohms for each degrees Celsius change in temperature. So what's that mean? Every time we go up, so if we go from 25 degrees Celsius to 26 degrees Celsius, we've raised 5 ohms. Alright, so what are we finding? We're finding the output voltage. So we have to find V out in this case. Okay, but first we need to figure out how many degrees have we moved. Because I've given you the value for the thermistor at 25 degrees Celsius, but it's actually sitting at 65 degrees Celsius right now. So we have to know that it has moved 40 degrees Celsius from where our basis is. So why do we need to do that? Because we have to find the new resistance. So since it's moved 40 degrees, and we know that we have 5 ohms of resistance for each degrees, we have to take 40 times 5. So 40 times 5 is 200. So we've increased 200 ohms. We don't use 200 ohms. We've increased 200 ohms. So our R1 up here started at 1,000 and it's now up to 1,200. So we've increased 200 ohms. So R1 is 1,000, which we started at, plus 200 because we went from 25 degrees to 65 degrees. So R1 is 1,200. It's very important that we use that. Now, for our scenario, we want to know that V out is VB minus VA. We always want to make sure that V out is positive. You can interchange those. It's just basically a polarity thing, so you're okay there. We're going to use a voltage divider to calculate VA. Remember, it's the voltage drop across R3. So we have to take R3 divided by R1 plus R3 times our voltage source. Our voltage source in this case is 9 volts. When we substitute in our values, we're going to get 1,000 divided by 1,200 plus 1,000 times 9, or VA is 4.09 volts. Okay, this is very important. We got to find the other calculation first. We have to find VB. VB is the voltage drop across R4, so we will use a voltage divider across R4 to calculate that. So it's going to be R4 over R2 plus R4 times the voltage source. So we're going to get 1,000 over 1,000 plus 1,000 times 9 volts, or VB ends up being 4.5 volts. Now lastly, we have to calculate V out. That's the whole point of this, is what's the output voltage here when we've changed the resistance on the thermistor. So this is how your thermostat works in your house. Alright, so V out is VB minus VA. So we're going to take 4.5 minus 4.09, and V out is 0.41 volts. So that 0.41 volts translates to some temperature. Alright, changing. So 65 degrees. That's really all that's really telling us. So when you turn your thermostat, now it's a little different here because 65 degrees Celsius is rather warm compared to Fahrenheit. So that's one's not necessarily as realistic for a temperature you and I would be using. Let's say we need to, we're cooking something or heating steel up or those sort of things. Then our temperature can be a little bit higher in that scenario. Alright, so these you don't have to write down. This is just others examples of where we use a Wheatstone bridge. So we've talked about it, a load cell, using stress and strain gauges on a scale. So when you get on, you're changing the value yourself. Alright, and how did those work? Well, you're standing on it puts strain on the resistance. So as you step with your force down on that resistance, alright, it's changing and making that value vary and then creating that output voltage, which translates into your weight. Okay, so just different ways of what they look like and where we put them you can use for, and it's doing other different calculations for us as well. But this is how all four apply, so on a scale or something like that. If you use a full bridge. A full bridge means every single one of those resistors is a variable resistor. Where the one we just did, it was a single. Okay, the calculation we did with the thermistor was single, but for a scale, okay, you're going to use a full bridge. Alright, so that was one method of calculating a series parallel combination circuit. This is another way we use a Thevenin's equivalent. So this is going to be a method. Remember at the beginning of the lecture we talked about getting a bunch of different series parallel combinations and writing them in terms of one circuit. This is what we're going to do when we do Thevenin's equivalents as well. Any two-terminal resistive circuit we can be replaced with a simple equivalent circuit. And we're going to give each one of those a Thevenin voltage, and we're going to calculate a Thevenin resistance. So I'm going to walk through how to calculate those. So the voltage is what we call a no-load voltage, so we remove the load resistance, and we calculate using a voltage divider. Then when we do the Thevenin resistance, okay, we short the terminals and calculate the resistance. If you know those two steps, doing a Thevenin circuit is not hard. Your solution will look exactly like what you see on the screen here. We have a Thevenin voltage and a Thevenin resistance. You're just going to calculate the values. Alright, so this is a snippet out of your book. Alright, you can go through that and read it. But we're going to do an example here that actually walks through it. So what we talked about, to find the Thevenin voltage, alright, we remove the load resistor, so that's always important. We're going to remove the load resistor, and then we are going to do a voltage divider across the specific resistor that the terminals would be on. Alright, we can neglect R3 in this case because the voltage drop would be the same because we've removed the load. So R3 does not play in what we're calculating here. Then in part B over here, we're going to replace the voltage source with a short and then calculate the resistance. The resistance does come into play here, alright, when we do this for our Thevenin voltage and our Thevenin resistance and relationship. But let's work through a problem here. We want to find what's the Thevenin voltage for this circuit. So notice we have RL, which is a load resistor, and then we have R1 and R2 in our voltage source. So the first step when we do these calculations is we remove the load resistor, okay, and then we're going to find the voltage drop across R2 because that's where the terminals are. So to find the voltage drop across R2, it's going to be R2 divided by R1 times the quantity Vs. Okay, so when we substitute those values in, we're going to get 27,000 divided by 10,000 plus 27,000 times 12 volts. So our Thevenin voltage, and we call it VTH, is 8.76. Remember, we're creating an equivalent circuit here. So we've done our Thevenin voltage. You remove the load resistor to do anything Thevenin. Remove the load. So cover it up like it's not even in there. Don't even draw it in the picture anymore. Then we have to find the Thevenin resistance we remove the load resistor again, we short the voltage. All right, so notice the voltage source here, we're going to short it just by making a connection. When we make that connection, R1 and R2 now have a relationship. They are now in parallel. Okay? R1 and R2 are now in parallel. So we still neglect the load resistor, and that equation, R1, R2 divided by R1 plus R2, remember that's the shortcut for two resistors in parallel. Normally you'd want to do R1 inverse plus R2 inverse, all completely inverse. It's the same thing, all right, but we end up getting 7.29 kilo ohms of resistance. So now our Thevenin circuit, our Thevenin resistance, which we say RTH, is now 7.29 kilo ohms. So the solution, we would draw it as this. On top, that's the original circuit, the original schematic of what we had. And the bottom is our Thevenin circuit, where we have found our Thevenin resistance and our Thevenin voltage. This kind of goes back to when we started in this lecture talking about, looking from a specific terminal, what does it see? We don't care what's inside the box. It sees one resistance and one voltage. So that's why we make this Thevenin circuit down. It's going to be very important for us when we do maximum power transfer, and that will really relate to like your speakers and things like that in your stereo. So you don't have to write all this one down. I just want to cover through this piece right here. We have Thevenin's equivalent. What it does is it really depends on the perspective of the terminal. I want you to think back at the beginning of the lecture when we had the delta, all right, and we did between A and B, B and C and D, and what the perspective was based on which terminals we were looking at. Thevenin will do the same thing, whether we want the Thevenin voltage between A and B, or between B and C, or between A and C. All right, so just know that the calculations are going to be different. I'm going to show you one here in a few minutes. This is a snippet right out of your book. All right, we're still removing like load resistors. It's just going to be how we actually handle that series and parallel combination. So let's take a look at this. All right, I'm going to give you this circuit here. We got 15 volt source. We have R1 and R2, and I want you to find the Thevenin equivalent between terminals A and B. So now, right, we're not grasping a big thing. It's between the specific terminals. Well, between A and B, what do we really want that Thevenin to be? We want it to be the voltage drop across A and B. So don't get scared of Thevenin stuff. Thevenin stuff's actually pretty easy. When we do Thevenin, okay, it's just the voltage drop. So our Thevenin voltage, our VTH, in this particular case, terminal A and B, it's just the voltage drop across R2. So it's going to be 22 divided by 100 plus 22 times our voltage source, which is 15. You can use the K's if you want and make it 100,000 and 22,000 if you want, but if you don't, it's okay. It'll still work out, okay? Because the thousandths piece cancels one another anyways. So our Thevenin voltage, if we set it up, ends up being 2.7 volts. Now we got to find our Thevenin resistance. Please remember, every single time we find a Thevenin resistance, we have to short the voltage source and then calculate the resistance. So in this case, when we short the voltage source, R1 and R2 are now in parallel. So we can use the shortcut, the R1 times R2 divided by R1 plus R2, because we only have two resistors in parallel. So when we do that, all right, and we get the value, we get 100 times 22 divided by 100 plus 22, and know that that's in kilo ohms, so we end up getting 18.03 kilo ohms. So now we found our Thevenin voltage, and now we found our Thevenin resistance. Now we can draw our Thevenin circuit. All right, that's the one at the bottom here, and that's our equivalent circuit. So the circuit at the top becomes the circuit at the bottom when we do our Thevenin equivalency. Let's do another one. Okay, we're going to go between terminal A and B, and terminal A and B is sandwiched in the middle there. We want to calculate the Thevenin equivalent for the following circuit across terminals A and B. Please make sure that you have this one in your notes. So draw this circuit out and write everything out step by step so that I can have it for you, and you can use it on your notes for your lecture quiz and those sort of things. Okay, so what do we got going on here? We got R1, R2, VS, we have RL in the middle. You should be thinking automatically now, we've done a few of these, we need to do what? Remove the load resistor. So first step, remove the load resistor. Then we find the thevenin voltage. All right, so right here, remove the load resistor. So now we have between terminals A and B. And we have to find what's the voltage drop across terminal A and B. It's what's dropping across R1. R1 is the resistor that goes across terminal A and B now. Alright, so it's the voltage drop across R1. So now that we've removed RL, the thevenin voltage is R1 divided by R1 plus R2 times Vs. So we're using a voltage divider once again to find our thevenin voltage. So it's going to be 100 divided by 100 plus 270 times 3. The 100 plus 270 is the 370. So our thevenin voltage is 0.812. Alright. Next, we have to calculate the thevenin resistance. Please remember, to calculate thevenin resistance, you must short the voltage source. Okay? We're going to short the voltage source. And now we have to see that the relationship between R1 and R2, they are now in parallel across terminals A and B. So we have to use the equation for parallel resistors. And when we do that, we get 72.97 ohms. Okay? So the circuit on top is our original circuit. The circuit below is our thevenin equivalent circuit. So, you don't have to write this one down. I just want you to know that we can use Thevenin's theorem for solving a Wheatstone bridge as well. Notice there's an RL. And we want to notice what? A to ground, B to ground. So we need to still find VA and still need to find VB. And we need to remember what the relationships look like between these circuits. First step, right? Pulling out RL. Okay, and then redraw the circuit. Use a voltage divider to calculate VA and VB. The difference between VA and VB, which we found before to be V out, is what your thevenin voltage is. That's all that is right there. Alright, so thevenin, V thevenin equals our V out. That's really all that is. Okay? So that's our V thevenin. Then what do we have to do? Short the voltage source. So we're shorting Vs. And we have to find the relationships between the resistors. Alright, so we can see that R1 and R2, how are they related now? R1 and R3, how are they related? They're in parallel. R2 and R4, how are they related? They're in parallel. Those parallel combinations are in series with one another, and that's how we get our thevenin resistance for the Wheatstone bridge. Okay? So I don't expect you to know that one, but I want you to know how we can use a thevenin to solve a Wheatstone bridge. Okay? And if you want to go through and you want to solve it on your own, you're more than welcome to. I'm going to give you all the solutions right here to draw it and work through it. But I want to get to maximum power transfer. Alright? Maximum power transfer is when this is a test question, and this makes the test question 1,000 times easier. When does maximum power transfer occur? When RL equals RS. When RL equals RS, where RS is the resistance of the voltage source and RL is the load resistor. When those two have the same value, that's where we have maximum power transfer. Very important, like in your car stereo system and things like that. That's why when you buy speakers and they have 8 ohm impedance, the 8 ohms that's coming out of your car stereo has to match the 8 ohms on the speaker that you plug into for your stereo, so that you can get the maximum power transfer. If your stereo is 8 ohms and your speakers are 4 ohms, you're not going to get maximum power out of your speakers. So hopefully that kind of relates for you guys when you do that. So what we want to know here is, what's the power delivered to the load? Will we have maximum power transfer? Absolutely, because RS equals RL. They're both 50 ohms. But we got to calculate, what's the voltage drop across RL to get the power there. Okay? The voltage drop across RL is going to be 5 volts. You should know how to do that, right? 50 divided by 50 plus 50, so we have 50 over 100 times 10. Okay, so we have half of 10, which is 5 volts. You should be able to kind of do that one in your head, but you can write it down. All right, we've done plenty of voltage dividers. So the voltage to the load is 5 volts. Now that we know the voltage across the load, we can calculate power, because we know power is what? V squared over R, using Watt's law. So we're going to use 5 volts squared divided by 50, and we get half a watt of power. So very, very important. I'm not going to do a ton of details on maximum power transfer. I think that stuff's fairly easy. But you should be able to calculate it, and I expect you to be able to do that on a test. Alright. Lastly, this one's going to take a little bit. We have superposition. It's another way to determine or simplify a circuit. But what we really want to do here, and when we apply superposition, this one's important. Superposition is applied when we have 2 power sources in a circuit at the same time. Notice this has 12 volts and 18 volts. So we want to find the contribution to the current I2 from the 12 volt source and the 18 volt source. So essentially we have to solve this circuit twice. Kind of a 4-step process. We're going to leave one voltage source alone. We're going to short it and do all the calculations for the current. And then we're going to calculate and short the other voltage source and do all the different calculations. We're going to find RT and the total current and those sort of things. And then we're going to combine the sources or the solutions together when we do that. Alright? So what we want to do, take the time, draw this circuit down, and we're going to find what's the current through R2. Notice there's 2 voltage sources. There's a 12 volt source and an 18 volt source. You're going to find the contributions from each source. So anytime you see 2 sources on your problem, you're going to solve using superposition right now. Okay, so take the time to draw this, and we're looking for I2, which is the current through resistor 2. Alright, so first step for us. So we go through this, we're going to find the contributions from voltage source 1. Voltage source 1 is the 12 volt source. So in order for us to do this, notice I've redrawn the circuit over here. We short the 18 volt source, or short source 2. And we're going to calculate I2. Okay, we're going to calculate I2. This is procedural, so you have to make sure that you pay attention. In order to find I2, we have to find IT. In order to find IT, we have to find RT. So the best thing that you can do in this scenario is find the total resistance. So this is a series parallel combination. Notice that R2 is in parallel with R3, and that combination is in series with R1. So written that out here, and I have RTS1. That means resistance total, or total resistance from source 1. Source 1 I'm deeming the 12 volt source. So when we do that, we've shorted the 18 volt source, and we have this relationship. So substitute in the values, and we find the total resistance based on source 1 at 6100 ohms. Okay, make sure you're following along and it works in your calculator just like it does on the screen here. Then we find the total current I for source 1. So ITS1 means the total current from source 1. It's going to be voltage source 1 divided by total resistance from source 1. So it's going to be 12 divided by 6100. Alright, so our total current from source 1 is going to be 1.96 milliamps. That's the total current from source 1. And you can see in the picture, in the schematic in the upper right hand corner, where I have that laid out. Okay, where does that help us? That helps us find everything we need to know, because we're looking for I2, right? We're looking for the current through resistor 2. Now we can either find a voltage drop across that, or we can remember how to use a current divider. Remember a current divider, we use the current through the opposite circuit that's in parallel. So that's why R3 is on top. So I'm going to have I2 S1. So it's I2, which is what we're looking through, contributions from source 1. So that's going to be R3 divided by R2 plus R3 times the total current from source 1. So you can plug in the numbers, and we should know that the current I2 from source 1 is 980 microamps. Alright? You get 0.0098. You got to put that, don't use 0.98 milliamps. convert it to microamps. So it's 980 times 10 to the minus 6, which is 980 microamps. So that's the current that the voltage source 1 of 12 volts contributes to that resistor. So we're half done with the problem. Now we have to solve the circuit again, but this time we're going to short voltage source 1 and redo all of our calculations using voltage source 2. So all the contributions from voltage source 2. You need to do the same type of calculations. We're going to find RT, we're going to find IT from source 2, and then we're going to use a current divider to find I2 from source 2. Okay, same steps, although things change around a little bit because we're coming from the other direction. But we short voltage source 1. So now when we short voltage source 1, R1 and R2 are in parallel, and that parallel combination is in series with R3. Alright, so hopefully you can see that piece. When we calculate this, alright, I'm just going to plug it in using the inverse method, so we get R3. You should be able to do this piece. This is a review of parallel circuits. And know that the total resistance from source 2 is 8,732 ohms. We use that to calculate the total current from source 2. Total current from source 2, and I've drawn it on the schematic up there where it is. It's voltage source 2 divided by the total resistance from source 2. So it's going to be 18 divided by 8,732, or roughly 0.00206 amps, or for us, we're going to say 2.06 milliamps. That's just the total current that's being contributed from voltage source 2. So that's why it's ITS2. So those subscripts, that way you really know that we're talking about source 2 there. Then we use a current divider to find the total current that's going through R2, because that's I2 and from the source 2 contribution. So that's why it's I2S2. Alright, it's R1 divided by R1 plus R2 times ITS2. Right, remember, using a current divider, we have to use the current going through the opposite resistor that we want, which is R1. That's why R1's on top. Okay, divided by R1 plus R2 times the total current in this system. So it's going to be 2,700 divided by 2,700 plus 6,800 times 0.00206. So we get 0.000585 amps for I2 from the source 2 contribution, or 585 microamps. So source 2, which is 18 volts, is contributing 585 microamps to I2. We're not quite done. Alright, we have the current through I2 contributed from each source. Alright, so what I have here is the original circuit on top, and then the circuit from source 1 on the left, and the circuit from source 2 on the right. Notice the direction of I2. Alright, so in this case, when we add these, we calculated these before, right? I2S1 is 980 microamps, I2S2 is 585 microamps. In order to find the total current through I2, we add these two together. So I2 is the current from source 1 plus the current from source 2. So when we do that, 980 microamps plus 585 microamps equals 1,565 microamps. Alright, so superposition is a little bit longer. This will be on your big test, okay? And it'll probably be on your final. Make sure that you understand. Rework this problem a couple of times, alright? That's how you study in engineering, by doing problems you've seen, working through them, and then doing more problems that you have the solutions to, so you can check yourself. Being a good engineer has to do with putting in time and not the bare minimum. Alright, these are a little bit more challenging, and you got to do a little bit more thought process. They're a little bit more time consuming. Okay, so you know, you got to take time in these courses. Alright, let's talk briefly about some troubleshooting. Just common sense stuff, analysis, understanding how the circuit works normally, and then find out when it's failing. Alright, decide on a logical set of steps to find the fault. All right, and measurement, follow steps, make a plan. All right, it's kind of funny. It was actually like 2 days ago before I was making this recording. I had a prior student call me up and ask me some electrical problems about he's working at a mechanic place, and they can get a window to go up, but they can't get the window to go down. All right, and you know, when they take the motor out, it works fine if they just hook it up to a battery, but then they put it back in the vehicle, and something's wrong. When the window goes up, it won't go down, and it's only getting 9 volts instead of 12. But it's one of those, you know, hey, I talked through them, all right? We went through this troubleshoot, because he called me up and asked me for some help. I'm like, hey, come up with a plan. Start isolating things, all right? So it does happen in the real world, but you got to have a plan, because he's like, hey, I'm lost. He's like, we did this step and kind of this step, but I gave him some other steps that he needed to do to kind of isolate, you know. They knew it wasn't the motor, but I'm like, hey, let's isolate it to specific sets of wiring and those sort of things. Check continuity, where's your volt, what's your current, you know, just different sets of steps. That's very, very important. All right, hey, and sometimes it's always good to get someone else's, you know, opinion as you're going through something as well, because you've been racking your brain on this, but someone else might bring a fresh idea. All right, so logically go through, you know, and analyze a problem. Come up with steps instead of just staying there and going, I don't know. Well, take it from the other approach. What do you know, and what can you apply? All right, and see what that helps you eliminate. Well, I know that it's not this. I know that it's not this. That means it could be this. And then attack it that way. All right, so come up with a thought process. So, just like all the other chapters, all right, I need you to make sure that you know all the key terms and vocabulary. All right, those will be important. Those will show up on quizzes, stuff like this, and this will also show up on your lecture quiz. So make sure you know the definitions for these guys as well, because some of you may not actually listen to the entire lecture when I'm giving you hints of how to be successful. Okay, so with that, I know this was a lengthy lecture, but this is probably the most challenging portion of this course as we move forward. But if you can get these, remember, take your time, work problems, work through it a couple times so that you solidify your thought process and what you're going to do and how you analyze these problems and break them down. You might have to watch the video multiple times. You might have to work the example multiple times. That's okay. That's what's going to make you a good engineer. Putting in the time. Because eventually you put in the time now and the work now, when you become an engineer, it becomes easier because your mindset is correct and you know how to solve problems. That's really why we put you through all these. It's learning how to think. It's learning how to think. You don't go out in the real world every day and just work through problems like this. It's teaching you how to think methodically, design, develop, troubleshoot, you know, problem solve, analyze, all those critical thinking skills that you need to have and develop. The younger you can have and develop them, the stronger you will be in your future. All right, but I will see you guys in lab. All right, make sure you're ready for your lecture quiz, have your notes, and all those goodies for you.